Okay, so the rest of Chapter 8 deals with the other two phases of matter, that is liquids and solids. And we're going to cover both of them in this lecture here. Liquids, one of the most important things we can know about them is how many liquids are volatile. And that means that even below their boiling point, they're going to be releasing small amounts of particles into the air in the gas phase. This happens because some of the molecules are moving slowly and some of the molecules are moving more rapidly. There is a distribution of different kinetic energies, and occasionally one molecule will, by random chance, collide in such a way that it achieves an escape velocity and leaves the bulk of the liquid. If you have a liquid that is open to the air, then it will perhaps all evaporate away without ever really boiling. And we'll get to what exactly boiling means in a minute. But this is why, for example, even in the winter time, you can hang wet clothes out and they will dry. It doesn't have to be 100 degrees Celsius for water to evaporate away. Now, if we were to, instead of having a chamber that is open to the air, if we were to put a lid on it, like this figure right, oops, wrong way, right there, okay? If we put a lid on it, then eventually the pressure of the liquid in the vapor phase is going to build up to the point where molecules from the gas phase will be coming back down into the liquid phase at the same rate that molecules in the liquid phase are leaving into the gas phase. It'll reach an equilibrium, and the partial pressure of that substance in the gas phase will be constant. We call that its vapor pressure, and the vapor pressure depends on the temperature. It's different for different liquids and for any given liquid at different temperatures. So give me a sec, sorry. This is figure 820, and figure 820 shows a number of different substances. Ether, for example, has a particularly high vapor pressure. Even at room temperature, that's approaching atmospheric pressure. And ethyl alcohol is in the middle, and then water is the lowest vapor pressure. You know, growing up in Utah in a dry environment, I always kind of considered water to be a volatile liquid. That is a liquid that easily vaporizes. In most other climates where the humidity is a little bit higher, people don't think of water as being quite so volatile. And from a chemistry perspective, compared to things like ether, alcohols, acetone, a lot of these other liquids that we use in chemistry, water is a non-volatile liquid. Anyway, when the vapor pressure gets to be equal to the barometric pressure, well, then the liquid is able to generate bubbles and create cavities within itself and fill them with vapor, and that is what we call boiling. Boiling is different. The boiling temperature is different for different substances, and you can see on this chart that the normal boiling point is just whatever temperature is required to bring that substance's vapor pressure up to 1 atmosphere. So for water, that's about 100 degrees Celsius. For ether, it looks like it's 34.6 degrees Celsius. For ethanol, 78.3 degrees Celsius. And that's the point where they'll begin to bubble and they'll begin to really vaporize at a fast rate. And it's impossible to get a liquid to a temperature that is above its boiling point. If you put in more and more heat, it will simply boil faster. It will eventually boil all the way at a faster rate. The temperature itself gets pinned at that value unless you, say, change the external pressure by putting it in a closed vessel. And something like a pressure cooker, an Instapot, is able to cook food at a higher temperature because it pressurizes the whole cooking chamber. So that's what boiling means, and all liquids will boil at their own unique temperature. You can also think about how that normal boiling point is really only applicable in locations that have an atmospheric pressure of 1 atmosphere. So here in Cedar City, where we have about 0.82 atmospheres of barometric pressure, our boiling point is lower. And looking at this chart, well, I don't know, it's going to be in the low 90s. Sorry. At one point I calculated it. I think it's around 91 degrees Celsius or so is what the boiling point is for water in Cedar City. And if you were to go up to the top of the Himalayas, then the boiling point would be lower still. There are other properties of liquids that are important. Sorry, there it goes. Okay. We've already talked about how the boiling point is a function of intermolecular forces. And so water having the highest normal boiling point out of those 3 examples tells you that water has the strongest intermolecular forces between them. The ethanol exhibits hydrogen bonds like water, but they're a little bit weaker. And the ether is only going to have dipole-dipole interactions. So its boiling point was the lowest. Well, these intermolecular forces will also control other properties of liquids, and one of them is viscosity. So viscosity, I'll go ahead and write that. Oops. Wanted to make sure I spelled it correctly. So viscosity is the measure of how freely a liquid flows, or rather it's the resistance to flow. A high viscosity fluid will be something like motor oil or even honey, where if you dump the honey bottle over, it's going to take a few seconds for it to drip its way out. That's because the molecules are actually sticking closely to each other with strong intermolecular forces. And it takes some time for the liquid to flow as a result. Then you can have low viscosity liquids like water will dump out right away, but alcohol or ether or dichloromethane, some of these organic solvents that you may encounter later in your schooling, have even lower viscosities than water. You might think, what can flow more freely than water? Well, if you handle these other liquids enough, you'll see that they definitely flow more freely than water. It's harder to hold them in a dropper pipette, for example. They'll spread over a surface sort of differently than water does, and that has to do with viscosity. And then there's one last property of liquids that depends on the strength of their intermolecular forces, and that is surface tension. So I've got a figure here to describe surface tension. Oh, there we are. So surface tension results from the fact that molecules on the surface of a liquid have neighbors around them and beneath them, but no neighbors up above. That's what it means to be on the surface. And so generally speaking, the attractive forces that the gas above them offer are going to be paltry or non-existent. And so it's less energetically favorable for a particle to be on the surface. The lowest energy configuration will be the configuration which gives as many molecules their full complement of nearby partners to provide these attractive intermolecular forces. So compared to a molecule down in the bulk, which has neighbors on all sides, a molecule on the surface is higher in energy. It's not as stable. And so the interesting result of this is that liquids will naturally form curved surfaces. If you think about for a given total volume of liquid, what shape is going to present the smallest amount of surface area? And that would be a perfect sphere. That's a geometrical fact. Thanks to the mathematicians, we know that to be a fact. And so a liquid is going to have one factor, the minimizing of its surface area, trying to pull it up into a ball shape. Of course, there are other factors as well. The fact that gravity is pulling the liquid downward, and in order to ball up, that has to lift particles up in the gravitational potential. And so liquids don't actually form a perfect sphere. They will have some sort of a rounded surface instead, and that is the result of the interplay between the surface tension and the influence of gravity. If you look at videos from like the International Space Station, for example, then all liquids do tend to form a perfect sphere because there's nothing that is competing against the surface tension trying to twist the surface into a perfect sphere in order to minimize its surface area. So surface tension is unintuitive in a couple of ways. Bubbles, for example, I sort of naively thought that adding soap to water must make the surfaces tougher because a bubble seems like it's kind of got this skin that must be pretty tough in order to remain intact. But when we think about surface tension, it's actually quite the opposite. We should look at bubbles and say, they have an enormous amount of surface area. They've got the whole area on the outside of the bubble, and then they have an almost equal amount of area on the inside of the bubble as well. So in order for a bubble to be stable, the water actually has to have a dramatically reduced surface tension, and that's what soap does. It will reduce the surface tension of water, which I thought to be a little bit unintuitive. You can also see this by taking a glass of water and put something like a paper clip on the top. If you rest the paper clip lightly on the surface of a glass of water, then the surface tension of the water will hold that paper clip up. But if you drop some dish soap into the cup, then immediately the surface tension will be reduced and the paper clip will fall through. Surface tension is stronger in some materials than in others, and you can sort of measure the degree of curvature that a substance is able to achieve under the influence of gravity and use that as a measure of their surface tension. So that is surface tension, which is our last property of liquids that we're interested in this chapter. We do have a section 8.13 that points out how water is a really novel and interesting substance with respect to all of these properties. It has an unusually high heat capacity, and we'll talk about heat capacity in just a moment. Basically, it means that it requires a lot of energy to heat water up and to cool water down. And that has the effect of stabilizing the temperature in parts of the world that are near large bodies of water. It's why the coasts of the country are warmer than the inland areas of the country. Water has very high surface tension. It has very high enthalpy of vaporization. It takes an incredible amount of energy to vaporize water, and that's a big part of the reason why water is liquid at room temperature. There aren't very many substances that occur naturally and remain a liquid under normal temperature and pressure conditions, so that makes water stand out. It has strong hydrogen bonding intermolecular interactions, which lead to all of these properties, and that also make water a good solvent for organic molecules. And of course, water being the primary solvent of our blood, our plasma, and everything else in our bodies, cytoplasm within the cells, it's important to our own biochemistry that water be this way. Water is also pretty close to unique in that its solid phase has lower density than its liquid phase. Most substances, as you cool them down, they contract a little bit in the liquid phase, and then when they freeze, they contract still more. And so the solid would drop to the bottom, it would sink, and that kind of makes sense with the idea that once the liquid particles are so cold that they stop moving, they're able to pack closer together. Water, however, when it begins to slow down and get close to its freezing point, instead of packing closer together, the water molecules begin to organize themselves into an open lattice structure, where the hydrogen bonding interactions between water molecules will become now hydrogen bonds in a ice crystal lattice. And this crystal lattice happens to be more spacious than water molecules themselves. Once they're held rigidly in place, they're not able to squeeze past and around one another. And so ice has a lower density than liquid water. Again, this is unusual. Most substances don't do that. And it's particularly important to our ecosystem because this property of ice floating instead of sinking means that in the wintertime a lake might freeze over the top, but that ice will remain on top and act as a sort of a blanket to the rest of the water beneath, and the lake won't freeze through solid. If ice sank to the bottom, then you can see how that would lead to new water being exposed to the cold air and freezing and sinking and freezing and sinking, and a lake would freeze straight through in the winter, which would really destroy the ecosystem of the lake. So, you know, water is really interesting. It's no coincidence that you know, life has taken advantage of all of these properties. That most life that has evolved on the earth has in some way leveraged the unique properties of water in its biochemistry in order to survive and thrive. And so that's it for liquids. Of course, there's a lot more about liquids that we could talk about, but in this course we're just looking at the most important fundamental properties of liquids. And now we go to solids. Sorry, one moment. So solids can exist in different forms. Many of them will exhibit an ordered structure over long ranges. What you're looking at here is a lattice of carbon atoms. And when carbon atoms organize themselves in this structured and orderly way, we call it a diamond. And so carbon can also organize themselves with slightly different patterns, and they become graphite or coal. And so these sorts of solids, which organize themselves over long ranges, are called crystalline solids. And just like ionic crystals, which are composed of cations and anions, crystalline solids like diamond, made entirely of nonmetals, can also have the sort of faceted, smooth appearance. They'll cleave along planes often. They're very strong and rigid, and they have great optical properties. Diamond is transparent and brilliant because of its crystalline nature. Now let me erase this here. We'll get rid of that picture of the diamond lattice. Okay, so crystalline solids are divided into four different types. The first are ionic solids. Ionic solids, something like sodium chloride, any ionic compound, they form a crystalline lattice, and we've talked about ionic compounds before. And then we can have molecular solids. So a molecular solid would be something like sugar. Now, sugar forms crystals. They're even faceted, and they form naturally with these flat surfaces and everything. They do form true crystals. However, within the crystal, each individual sugar molecule is still unique and has its boundaries. And you can look at a microscopic picture of a sugar crystal and say there's one sugar molecule, there's another sugar molecule, etc. Ice would be another example of this. So we'll say sugar or water ice. These are molecular solids. So any molecule which you can sort of start in the liquid phase and freeze it down into a solid is likely to form a molecular crystalline solid if it crystallizes. Okay, the third are the covalent network solids. Diamond is an example of a covalent network solid. And let me put the diamond back up again. This isn't a collection of different molecules of carbon that have intermolecular forces. This is rather a network of carbon atoms that are all covalently bonded to all four of their neighbors. You could think of a diamond as one giant molecule because there are covalent bonds from one end to the other. Let me contrast that really quickly with the water. So water here would be a molecular solid, and you can see individual water molecules in this crystalline structure. Water is a molecular crystalline structure, and diamond is a covalent network crystal. And then finally we have metallic solids. So metallic solids are made up entirely of metals. It could be a pure metal like copper or silver, or it could be an alloy or mixture of metals like brass and bronze. But the metals will also arrange themselves into a regular crystal pattern. It's different than covalent network because they are not held together by covalent bonds. Metallic bonds are not as rigid. You can, with a hammer, reshape a metal into a new shape. You could stretch it out into a wire or pound it out into a thin film. Metals are malleable and ductile are the words we use to describe those processes. And the bottom line is that metallic crystals are held a little bit less rigidly. You can deform them, but they always settle into the same overall pattern. Maybe you've just shifted the atoms one or two places with each blow of the hammer. And so these are held together by metallic bonds. Molecular and covalent network crystalline solids are held together by covalent bonds. Covalent network has covalent bonds spanning the entire bulk of the substance. Molecular compounds have covalent bonds holding molecules together, and then the molecules arrange themselves by intermolecular forces. And ionic compounds are held together by ionic bonds. The next type of solid is different from a crystalline solid altogether. That is an amorphous solid. And so amorphous solids on the microscopic scale just don't show that regular orderly structure. If you think of looking at a liquid on the microscopic scale, it's going to be a bit chaotic. Molecules are going past one another, they're jostling one another, bumping and bouncing and twisting and turning, and it looks a little bit chaotic. Now an amorphous solid is a liquid that has cooled down and solidified so rapidly that the particles were not able to rearrange themselves into a regular lattice. Instead, they just got frozen in place in that chaotic arrangement. And so amorphous solids are really different than crystalline solids in lots of important ways. They show no long-range structure on the microscopic scale. The consequence of that is that when you heat up an amorphous solid, parts of it will melt before other parts of it on a microscopic scale. And this means that the solid will begin to soften, and it will go through this soft intermediate phase before it really melts. Glass is a prime example of an amorphous solid, and hopefully you can sort of imagine a glass blower will take some solid glass, stick it in the furnace, and take it out, and it will be flexible, and they can shape it, and they can do art with it or make glassware with it. And that's because glass is an amorphous solid that gets soft within a certain temperature range. Now contrast that with ice, a crystalline molecular solid. If you take ice out of the freezer and you warm it up, it doesn't ever become soft. You can't ever like shape ice like Play-Doh. It's either a solid or it's a liquid, and there's no like soft middle ground. It will be a solid up until it reaches the temperature where it melts, and then it will melt into a liquid. And I think that's the most intuitive way to sort of recognize the real difference between amorphous and crystalline solids. Glass is a common example of a amorphous solid. And glass is made out of the same materials, silicon and oxygen, that will form crystalline solids like quartz. So the only difference between quartz and glass is the orderliness of the oxygen and silicon on the microscopic level. And they're formed by cooling down under different circumstances and at different rates. So sugar also, you can make sugar crystals. You can make candy by crystallizing sugar, but you can also make toffee and caramel, which is pretty much an amorphous form of sugar as well. Okay, so when a substance undergoes a phase change, it'll either give off heat or take in heat to do so. And so if I go from a solid to a liquid, or from a liquid to a gas, that's an upward phase change. It will require energy to make that transition. If I go from a gas to a liquid, or a liquid to a solid, it's a little less intuitive, but just as real, that process will release a certain amount of energy as the phase settles down into the next lower level. So we'll call this amount of heat the enthalpy of fusion. So the energy required to convert from a solid to a liquid we call the enthalpy of fusion, or the enthalpy of vaporization. So fusion is solid to liquid, vaporization is liquid to gas, and then if you go the other direction, you just take the negative value. Right? So if enthalpy of fusion for water is 334 joules per gram, then the energy that would be released as the liquid goes to freeze into a solid would be negative 334 joules per gram. And so we'll know that Q, the heat that is required to undergo a phase change, is going to equal the mass times the delta H of fusion or vaporization, depending on which phase change you're looking at. And then we can also talk about heat that is required for changing temperature within a phase, and that is going to equal m times c times delta T. And so this would be the mass of the substance. C is the specific heat, and that is a number that is unique to each substance. It tells how much energy is required to raise 1 gram of the substance by 1 degree Celsius. And then delta T is the temperature change. We can talk about temperature changes, therefore, as in terms of a heating curve. So let me pull up our last figure for the day. So this is a heating curve. You see on the x-axis we have the amount of heat that was added to our sample, and on the y-axis is the temperature. And so if you start over here, you have a solid, sorry, it looks like it's at about negative 75 degrees Celsius. Okay, and as you add heat to that solid at negative 75 degrees Celsius, then the temperature is going to increase. And so the increase in temperature for the amount of heat is going to obey this equation right here. And then once you reach 0 degrees Celsius, even though you're adding heat, the temperature remains constant. And this is a sign that the substance is undergoing a phase change. And so that region of the heating curve is going to be governed by this equation right here. The temperature won't rise again until that phase change is complete, and the amount of heat that will require depends on the mass and the enthalpy of that phase change. And then you're in the liquid phase now, and you see adding heat again causes the temperature to rise from 0 to 100 degrees, and then we see another plateau. And so that temperature rise from 0 to 100 degrees will be governed by this equation. The plateau is another phase change, this time vaporization from liquid to gas phase, and you'll notice that plateau is rather substantial in this case. It plateaus for a while until the total amount of heat required to undergo that phase change is added, and now it'll all be in the vapor phase. And if you continue to add heat to the vapor, then its temperature will rise again according to this equation here until the end of the graph. So this sort of a heating curve is exactly what we're going to end with. I want to do a practice problem and then we'll be done. So 7.5 grams of water begin at negative 6 degrees Celsius. So we want to take 7.5 grams of water at negative 6 degrees Celsius, and we want to know how much energy is required to convert that to 125 degrees Celsius, and at that point, of course, it will be steam, no longer water. And so if I could draw a heating curve, just like the heating curve that we saw in the figure, we'll put the temperature as the y-axis, and then Q represents the amount of heat added. Then we'll start here at negative 6, and we'll increase from negative 6 degrees Celsius to 0 degrees Celsius. And then the ice will melt. And then it will begin to increase again from 0 to 100, and the water will boil. And then after the boiling is done, we'll continue to heat that steam until we reach 125 degrees Celsius, which isn't a special number at all, it's just the ending point for our particular problem. And if we want to know exactly how much heat is required to undergo this entire journey from ice at negative 6 to steam at positive 125, we're going to have to calculate each of the legs of this journey independently. So we'll call this warming of the ice, step 1. The melting of the ice is step 2. The warming of the water is step 3. The boiling of the water is step 4. And then finally, the warming of the steam is step 5. And so let me quickly show you. Here we have collected all of the different values. The specific heat of water in the ice phase or the liquid phase or the gas phase is different. And there are the enthalpies of fusion and the enthalpies of vaporization. So let's go ahead and just calculate each of those different steps. Q1 is the warming of the ice, and so we'll use mc delta T. In this case, m is 7.5 grams. The C for ice is 2.11 joules per gram degrees Celsius. And we're going to raise the temperature by 6 degrees Celsius. And this is going to require a total of 15.8 joules. That can't be right. I made another mistake. Look at me. Sorry, I'm going to solve this again. 7.5 times 2.11 times 6. I probably just forgot the 6. So that's going to be 94.9 joules. For Q2, now this is the melting of the ice, and so we're going to use Q is equal to m times delta H. The mass is still 7.5 grams, and the enthalpy of fusion is 334 joules per gram. There's no degree Celsius here because there's no delta T in the formula. It's just m delta H. So 7.5 times 334, that's going to equal 2,505 joules. Q3, now this is the warming of the liquid water. Q3 is going to equal 7.5 grams, that's the mass, times 4.18 joules per gram degrees Celsius, that's the specific heat of liquid water, times 100 degrees Celsius. And that's because we're going to increase the temperature of the water from 0 to 100. That's a total change in temperature of 100 degrees Celsius. And that should equal 3,135 joules. Now Q4, the vaporization or the boiling of the water. Q4 is going to equal that same mass, 7.5 grams. And the enthalpy of vaporization is a whopping 2,260 joules per gram. So this is going to be 16,950 joules. Much larger number than anything we've seen so far. And then lastly, that fifth leg, the warming of the vaporized water, or the steam, is going to follow, again, this equation, Q equals mc delta T. So Q5 is equal to 7.5 grams, and the specific heat of water vapor is 2.00 joules per gram degree Celsius. And we're going to increase the temperature from 100 to 125. That's a total delta T of 25 degrees Celsius. And this ought to equal 375. 375 joules. Now I'm sure my number's wrong, so let me calculate the real number here real quick. That's 94.9. 94.9 plus 2505 plus 3135 plus 16950 plus 375. That should be 23,000. 23,000 joules if you only have the 2 sig figs, or 23 kilojoules. And 16,950, or more than 2/3 of that, was expended in the vaporization stage. And that's why, if we can actually go back to this figure of the heating curve, that's why the vaporization plateau is so long. It takes such a tremendous amount of energy to vaporize that water. Okay, and that actually completes chapter 8 for us. So on Thursday we'll start into chapter 9. And I hope you enjoyed this video.